Okay, welcome to 15.4, Increasing Exponential Functions. All right, so exponential functions have exponents in them, and you're going to need this warm-up to do this lesson, so do it neatly. Write the problem and the answer. You'll be thankful you did. 2 is 2 times 2 times 2 is 2. 2 squared is 4. 2 to the first is 2. Everything to the 0 power is 1. Now, negative exponents, what do they make? Right? They make reciprocals. So this is 1/2. This is the reciprocal of 2 squared, 1/4. Right? And this is the reciprocal of 2 cubed, or 1/8. 3 cubed, 3 times 3 times 3 is 27. 3 squared is 9. 3 to the first is 3. 3, everything to the 0 power is 1. Negative exponents make the reciprocals. So in the news lately, you've hopefully been hearing about exponential growth. We're going to do the mathematics of exponential growth. When in the general public, they use exponential growth as something getting bigger really, really fast. And you're going to see that in the graph today. So this is the math for an exponential function. B is the base of the function, and then the x is going to be, so x is in the exponent, all right? That's easy to remember. So we're going to graph our very first one, f of x equals 2 to the x, is how you say that. So it's y equals 2 to the x. And you already did the math. That's why the t-table is already filled in, right? 2 to the negative third is 1/8. 2 to the negative second is 1/4, and so on. So plot those points. They're going to come out in an exponential curve. So -3, 1/8, well, that's almost right on the x-axis. -2, 1/4 is 1/4 the way up to 1. -1, 1/2 is half the way up to 1. 0 goes to 1. 1 goes to +2. 2 goes to 4. And 3 goes to 8, way up there. I think I've already plotted it. There is the exponential function f of x equals 2 to the x. So we have been increasing things linearly up until now, right? But when things increase exponentially, they increase way faster. So we're going to show that to you. So we're going to evaluate this function, these two functions, for x equals 3. Let's see that. So f of 3 here, this is a linear function, right? And is just 6. So at 3, it's, right, at 3, it's here at 6. For f of 3 for the other one, though, 2 to the third is 8. So when x is 3, you're at 8. And we can compare those two. Now let's look at the other. Let's evaluate it again for x equals 6. So f of 6 for the linear one is just 2 times 6, or 12. So when it's at 6, this one is at 12. Now compare that to the other one. For the other one, for the exponential curve, f of 6 is 2 to the 6th, which is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 64. It's at 128, right? 4, 8, 16, 30. Oh, did I do it wrong? Let's make sure I did it right. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Oh, 64, my fault. So it's off the graph, right? Either way, it's off the graph by 6. We're a long way from being off the graph on the linear function. Now, what about the small side, right? so I've blown up part of the graph so we could see it better here. That's what that's about. And so let's try to graph a few points here. So we're going to graph x is negative 4. So 2 to the negative 4th, right? So that's 1 over 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. Right, so this is 1/16. So when x is negative 4, now we're at 1/16, right? We'll try to graph that. It's right there. Now do f of negative 5. Well, f of negative 5 better be 1. We need 1 over 2 to the 5th, which is 1/32. So we're getting even closer to the x-axis there. And f of negative 6 be 1 over 2 to the 6th, or 1/64. And we're getting even closer. Probably you'd actually have to draw it on there to draw it on a piece of paper. But the question is, if I do f of negative 100, do I ever get to the x-axis? And the answer is no. It will get closer and closer. You won't be able to graph it unless we really blow up the graph so you could see it better. But it will never actually reach the x-axis. It gets closer and closer and closer each time. It closes the distance between itself and the previous point. It's half closer, right? It goes from 1/8 to 1/16 to 1/32, but it never gets there. And that concept is called asymptotic. Asymptotic is how you write that. And so the line it's getting closer to, in this case the x-axis, is called an asymptote. Now I know that sounds like a funny word, but that's what it's called, an asymptote. All right. So when we were doing linear functions, they had a constant amount they increased by, called the slope. These increase by a constant ratio. In the ones we just did, things were getting twice as big. So B is that constant ratio. So let's see that. So here's a table, and we're going to write the function for this. So the function is f of x, right? And each time we're not going right up by a constant amount, we're going up by 4 times the previous amount, right? The ratio here is 4. And so this is the function f of x equals 4 to the x. Put some numbers in there and you will see, right? 4 to the 0 is 1, 4 to the first is 4, 4 to the second is 16. It's going up by a constant ratio 4. It's 4 times the previous amount. All right, try this one. Yes, this is f of x equals 5 to the x. Every combination there is 5 times the previous one. Now I've moved things around here, but it's still the same thing. This is just a different part of the one above it. It's the same one as the one above it, but I'm showing you a different part of it, right? 1/16 times 4 is 4/16, also known as 1/4. 1/4 times 4 is 1, and obviously 1 times 4 is 4, and 4 times 4 is 16. The constant ratio here is 4. Well, 1/36 times what makes 1/6? Well, 6. Cancel. 1/6 times 1 what makes 1? 6. And obviously these are 6. So f of x here equals 6 to the x. So I want you to look at all these tables now and find the y-intercept in all of them. Right? Where does the y-intercept always occur in a graph? Where x is 0, right? It's the point where the graph crosses the y-axis, and that always happens at x equals 0. They're all the same. Yeah. It turns out the y-intercept is not in the same spot in a exponential function as it is in a linear function. It's in a different spot. but it does all of the ones we've done so far, the y-intercept was 0, 1. Look back at the other graphs. All right, so now we're going to do one where the y-intercept is not 0, 1. It turns out the y-intercept is that number right there, a. Right? Usually when we do linear functions, right, when we did linear functions, right, the y-intercept was out there. And when we did absolute value functions, right, absolute value, we didn't do one that complicated. If you did the absolute value of x plus 5, the y-intercept was out here. It's totally different for exponential functions, so be aware of that. So let's graph this one. F of x equals 4 times 2x. Right, now x rules of order of operations, you got to do the exponents first. So this would be 4 times 2 to the 0. Everything 0 power is 1. 4 times 1 is 4. All right, fill in the rest of the table. 4 times 2 to the first. 2 to the first is 2. 4 times 2 is 8. 2 to the second is 4. 4 times 4 is 16. 4 times 2 cubed. 2 cubed is 8. 4 times 8 is 32. 2 to the fourth is 16, and 4 times 16 is what? It's 128, yes? Yes. So let's graph those points. So 0. Now notice 4. So there's our y-intercept. Yeah, that number out there is our y-intercept. Right? Before this, the number out there was a 1, and we didn't write, just like we don't write 1 coefficients always. That's still a rule. So we haven't been writing it, but it's been 1, or 0, 1. And here, the y-intercept is 0, 4. And instead of calling, it's confusing, because normally we call the y-intercept b. Now we're calling the y-intercept a. It's tradition, not my fault. All right, so there are the points that we just plotted, right? And we could draw an exponential curve through that. Exponential functions are curved everywhere. There is no straight part. And there it is, a little bit better. Okay, so we're going to use this formula, and we're going to do what we just did. We're going to write an exponential function for each of these. So it's f of x, right? So what's the y-intercept? 0, 5. What's the constant ratio? Well, 5 times 3 is 15. 15 times 3 is 45. Yeah, 45 times 3. So this is 5 times 3 to the x. Now you can write this with the parentheses like this if you want. All right. In fact, let's do that. Right, but you would know either way you write that, you would do exponents before you do multiply. All right, so write this one. The y-intercept is 0, 7, so 7 goes there. The constant ratio it's going up here is 2. So this is 7 times 2 to the x, or 7 times 2x. There's the y-intercept. I moved it. Right? Y-intercepts occur where x is equal to 0 on every graph, always, not just these. So we have 6, and the constant ratio here looks like 2. 3 halves times 2, 3, yeah, it is. So this is 6 times 2 to the x. All right, so now we're going to be able, the standard is that you're going to be able to compare exponential functions to linear functions. So we are now bringing back the very beginning of the year. So one of those is exponential, and you're going to write an exponential function, and one of those is linear. See if you can figure it out. Well, there's our y-intercept. The y-intercept of both of these is the same. This one, we are multiplying by 3. This one, we are adding 9. Right? So write a linear function for both of those. Oh, no, and a function. Linear for the linear one, exponential for the exponential one. So this one is f of x equals 3, that's for this 3, times 3 to the x. That's an exponential. The linear one, well, the slope here is 9, right? It's going up by 9, and the y-intercept is 3. Very different function. All right, so one of those is exponential, one is linear. Figure out which is which. Well, this one, we're going up by plus 3. This one, we are multiplying by 2. Oh, I should write what the question was. So in this one, this is the exponential, right? This is the exponential. And this is linear. And this is linear. Let's write the functions again. The exponential, the y-intercept is 7. It's going up by 2. So 7 times 2 to the x. Here, the slope is 3, right? For those who've forgotten, right? To find the slope, you subtract your y's, you subtract your x's, right? The slope is 3, and the y-intercept is 0, 7. So it's f of x equals 3x plus 7. Linear versus exponential. So same thing. Let's practice. What was that funny word that describes a function that approaches a line? In this case, it was the x-axis, but never reaches it. I got to remember how to spell it. Asymptotic is how you say that. Asymptotic. The line that it's reaching is called an asymptote. Yeah, 64 times 8 is 512. There's our y-intercept. So this is a simple one. Right? It's 1 times 8 to the x, but you don't write that. Right? So you write f of x equals 8 to the x. That's the ones we started with, where the y-intercept was 0, 1. Right, and the constant ratio has to be the same everywhere, so you can just do the easy ones. But 1/18 times 6 is 1/3. So this is 2 times 6 to the x.